Hey, what's up guys? It's Pedro here from noobcoder.com, and in this tutorial we are going to be going over AVL trees in JavaScript. So, to get started, an AVL tree is basically a balanced binary search tree. More specifically, a height balance tree. So during my BST video, a major con that I pointed out is that it can be skewed to the left or right side. Having a skewed tree like this will give poor lookup, deletion, and insertion times, because at this point it's basically a linked list. So the first question we should ask ourselves, how do we fix this problem? Where here's where an AVL tree comes along. So what does being height balanced mean? Taking a look at the definition, a height balanced tree is a tree in which the left and right subtrees of every node differ in height by at most 1. Quickly reviewing what height is, the height of a tree is the longest path from our root node to its farthest node. So in other words, we're only counting the number of edges from the root to its farthest leaf node. The height of a tree with one node is said to have a height of 0, since it has no edges, and the height of a tree that's empty is said to have a height of -1. Alright, so enough talk. Let's go ahead with an example. So let's say I was given the following tree. So looking at this tree, taking a look at the left subtree, the left path has a single edge. The right path has a single edge. So since they are both 1, the height of the left subtree is 1. Taking a look at the right subtree, the height is 0, since it's a single node. Since there's a height difference of only 1, that means that this tree is considered height balanced. Now let's say that I want to add a single node to the left subtree. Taking the left height, we get 1, 2. So the left height is 2, and the right subtree's height remains unchanged because we haven't changed anything on that side. So now we have an unbalanced tree, because the left is 2 and the right is 0. So the difference in height between the two subtrees is more than 1, making it an unbalanced tree. Another way you could think about this is by levels. So let's go back to our original tree. If we show the levels, the left subtree has a node on level 2. And the right subtree has a node on level 1. So the difference in levels is only 1, thus this is a balanced tree. And if we were to go back to our unbalanced tree, you see that the left subtree has a node on the 3rd level, and the right subtree has a node on the 1st level. So we have a level difference of 2, so this is unbalanced. Now that we know what is considered a balanced tree, the next question should be, how does an AVL tree determine whether or not the tree is balanced or not? An AVL tree can achieve this by something called the balance factor of a node. Now the formula for this is pretty simple. The balance factor of a node is the height of the left subtree minus the height of the right subtree. You can also do the reverse of this. So you can also do the height of the right subtree minus the height of the left subtree. It doesn't matter. Now in order for this to be balanced, the balance factor of every node within the tree must be within the following set. So it has to be either -1, 0, or 1. Now, you can also think of this another way. You just take the absolute value of the left minus the right. And this has to be less than or equal to 1. So these two statements are equivalent. Alright, so now that that is out of the way, let's take a look at an example. So let's say I'm given the following tree, and I want to calculate the balance factor of each node. So let's start from the bottom and go to the top. So here, what is the height of the left subtree? Well, the left side of this node is empty. So the height of the left subtree is -1. What's the height of the right side? Well, this is also empty. So we get -1 as well. So using the balance factor formula, we take the left minus the right. So this node has a balance factor of 0. From this, since this is a leaf node, we can also assume that the balance factor of the other leaf nodes are also 0. Moving on to this node, we check the left subtree, and since this subtree only has a single node, we get a left height of 0. Checking the right side, we get the same thing, a single node, so the height of the right subtree is also 0. 0 minus 0, so we get a balance factor of 0. Next, let's take a look at this node. We check the left subtree. It has a single node, so we get a height of 0. Checking the right subtree, it's an empty tree, so the height of the right side is -1. 0 minus -1, so we get a balance factor of 1. Finally, let's take a look at this node. Taking a look at the left side, this node has a left and right subtree. So on the left side, we have 1. On the right side, we also have 1. So since they are both the same, the height of the left subtree is 1. Looking at the right subtree, we have 1. So the height of the right side is 1. 1 minus 1, so we get a balance factor of 0. So since the balance factor of all nodes within this tree is within the acceptable values within the set, so either -1, 0, or 1, that means that this is a balanced tree. So now let's have some fun. Let's go ahead and insert another node here. So now we have to recalculate the balance factor of every node within this path, because we added a node, thus affecting the height. And since our balance factor is dependent on the height, we need to redo the balance factors. So the newly inserted node has a balance factor of 0, since it's a leaf node. Looking at this node, the left subtree is empty, so the left's height is -1. We look at the right subtree, and it has a single node, so we get 0 for the right. And then we do -1 minus 0, so we get -1 as the balance factor. Checking the height of the balance factor of this node, we get the height of the left subtree. So we have a height of 1. We check the right subtree and it's empty. So the right side has a height of -1. So we get 1 minus -1, which gives us a balance factor of 2. So since this node's balance factor is not -1, 0, or 1, this tree is considered unbalanced. Last node, looking at the left subtree, the left side is 1. The right side is 1, so the height of the left subtree is 1. Taking a look at the right subtree, we get 1, 2. So the height of the right subtree is 2. So we get 1 minus 2. So we get a balance factor of -1. Alright, so now that we know how to calculate the balance factor of a node to determine whether or not a tree becomes unbalanced, the next question should be, how do we make an unbalanced tree balance again? So the way that an AVL tree accomplishes this is through rotations. To get started, there is a total of 4 cases to handle. So let's go over the first case. Let's say that I was given the following tree as the initial starting point. The numbers above each node is the balance factor of the node. So right now our tree is height balanced because all the nodes' balance factors are within the following set. And now let's say that I want to add 25 to this tree. So adding a node to an AVL tree is the same exact process as a binary search tree. An AVL tree is just a height balanced binary search tree. Adding 25 to this tree, 25 is less than 75, so we go left. And 25 is less than 50, so we can insert as the left child of 50. Calculating the balance factors, a leaf node always has a balance factor of 0. This node now has a balance factor of 1, and our root node now has a balance factor of 2. So since 2 isn't part of the set, this tree is unbalanced. So this is considered a left-left case, since we inserted the node within the left subtree as the left child, and the tree becoming unbalanced because of it. Now the question becomes, how do we take this tree and make it balanced again? We can accomplish this by using a right rotation. So we want to rotate to the right side of the imbalanced node. In this case, this is the root node. So everything gets shifted or pulled towards the right side of this node. So 75 becomes the right child of the root. 50 becomes the new root, and 25 remains the left child of 50. Recalculating the balance factor of the nodes after rotation, the leaf nodes always have a balance factor of 0, and calculating the root, we also end up getting 0. So therefore our tree is now height balanced. Moving on to the next case, let's say we start off with the following tree, and I want to insert 75 within this tree. So is 75 bigger than 25? Yes, it is. So we go right. Is 75 bigger than 50? Yes, it is. So we insert as the right child of 50. Calculating the balance factors, the newly inserted node has a balance factor of 0. This node has a balance factor of -1, and our root node has a balance factor of -2. So since -2 isn't within the set, once again, this makes our tree unbalanced. So since we inserted a node in the right subtree as the right child, This case is called the right case. Now, in order to make this tree balance, we need to perform a left rotation around the imbalanced node. In this case, it's the root node. So everything gets shifted or pulled towards the left side of this node. So 25 becomes the left child of the root, 50 becomes the new root, and 75 remains the right child of 50. Recalculating the balance factors, the leaf nodes always have a balance factor of 0, and the root node also has a balance factor of 0. Therefore, the tree is height balanced again. So far, we covered the left and right cases. Let's move on to another case. Let's say that we were given the following tree, and let's say that I want to insert 65 into that tree. Is 65 less than 75? Yes, it is. So we go left. Is 65 less than 50? No, it's not. So we insert as the right child of 50. Calculating the balance factors after insertion, the newly inserted node has a balance factor of 0. This node has a balance factor of -1, and our root node has a balance factor of 2. So since 2 isn't part of the set, this tree has become unbalanced. Now, since we've inserted this node within the left subtree as a right child, this case is called the left-right case. Now, in order to solve this problem, we should break it down to a form that we already know how to solve. So we know how to solve a left-left and a right-right case. In the case of a left-right case, we should turn it into a left-left case. So in order to achieve this, we need to perform a left rotation around this node. So we should get the following. 65 becomes the parent, and 50 becomes the left child of 65. Taking a look at the result, this kind of looks like a left-left case now, right? Calculating the balance factors, the leaf node is 0. This is 1, and the root is 2 now, exactly like our left-left case. So this tree is still unbalanced. So we perform a right rotation around the imbalanced node. 75 becomes the right child of the root, 65 becomes the new root, and 50 remains the left child of 65. Once again, let's calculate the balance factors. The leaf nodes are always 0, and our root is also 0. So this tree is now considered height balanced. So in the case of our left-right example, we had to perform a double rotation. First, we rotated left, and then we rotated right. Last case, let's say we start off with the following tree. And let's say that I want to insert 35. Is 35 bigger than 25? Yes, it is. So we go right. Is 35 bigger than 50? No, it's not. So we insert as the left child of 50. Recalculating the balance factors, leaf nodes have a balance factor of 0. This has a balance factor of 1, and our root node has a balance factor of -2. And since -2 isn't part of the set, this tree is considered unbalanced. So since this node was inserted within the right subtree as a left child, this case is called the right-left case. Now, in order to solve this, just like our left-right case, we should convert this into a form that's familiar to us. So let's perform a right rotation around this node. So we should get the following. 35 becomes the parent, and 50 becomes the right child of 35. Taking a look at the result, this kind of looks like a right case now. Calculating the balance factors, the leaf node is 0. This node is -1, and the root remains at -2 now, exactly like our right case. So this tree is still unbalanced. So we perform a left rotation around the imbalanced node. 25 becomes the left child of the root, 35 becomes the new root, and 50 remains the right child of 35. Once again, let's calculate the balance factors. The leaf nodes are always 0, and our root is also 0. So this tree is now considered height balanced. So in the case of our right-left example, we had to perform a double rotation. First, we rotated right, then we rotated left. Alright, so we covered all 4 cases, but what we haven't covered is what happens if these nodes have children. So in other words, these nodes have their own left and right subtrees. So this is our standard left-left case, and we perform a right rotation. So we get the following. X's right subtree remains on the right, Z's left and right subtree remain untouched. But what happens to Y's right subtree? Because Y already has a left and right child at the rotation. Well, Y's right subtree now becomes the left subtree of x. Taking a look at our right case, we perform a left rotation and get the following. X keeps its left subtree, Z keeps its left and right subtree, but once again, Y's left subtree has nowhere to go, since Y already has a left and right child after rotation, while Y's left subtree now becomes the right subtree of X. Moving on to our left-right case, we first perform a left rotation. So Y keeps its left subtree, Z keeps its right subtree. Once again, we need a place for Z's left subtree to go. So we insert on the right side of Y. Performing a right rotation now, we get the following. Y keeps its subtrees exactly as they are. X keeps its right subtree. However, we need a place for Z's right subtree to go, since it already has a left and right child after rotation. So Z's right subtree gets inserted as the left subtree of X. Last case, moving on to our right-left case, we first perform a right rotation. So Y keeps its right subtree, Z keeps its left subtree, and once again we need a place for Z's right subtree to go, since Z already has a left and right child. So Z's right subtree gets inserted as the left subtree of Y. Rotating left now, we get the following. X keeps its left subtree, Y keeps both its subtrees intact. However, we need a place for Z's left subtree to go, since it already has a left and right child after rotation. So we get Z's left subtree as the right subtree of X. Alright, so from here, let's start going over the code. So we'll go over our constructors first. So we're going to have two classes, a node class and an AVL class. Going over our node constructor first is going to be the same exact code as the code within my binary search tree video, except that we need to add a height property. This height property will be used to calculate the balance factors of the nodes. So we'll initialize this height property to 0, since a single node has a height of 0. Moving on to our constructor for our AVL, we just set the root node to null. Going over some utility methods within our node class, we have our getHeight method, which has a node param. So if the node is null, we'll just return -1 because that's an empty tree. Otherwise, we'll just go ahead and return the height of the node. Going over the getBalance method, we also have a node param, and we just return the balance factor of the node, which is just the left height minus the right height. Now, let's talk about the code for our rotations. Going over the left rotation first, we take in X as the param, where X is the node we're rotating around. First, we need to save the right child of X, and then we need to save the left child of Y. Performing our rotation now, we set the left child of Y to X, and X's right saves Y's left subtree. Afterwards, we need to recalculate the height values of X and Y, since they both have different subtrees which may affect the height. And then we go ahead and return this subtree, so the changes we made will be saved as the left or right child of a parent node, or might even be saved as the new root node. Moving on to the right rotation, pretty much the same thing as our left side. We take in a param X, where X is the node we're rotating around. First, we save the left child of X, and then we save the right child of Y. Performing our rotation now, Y's right child references X. X's left saves the right subtree of Y, and then we go ahead and recalculate the height of X and Y. Once we've updated our heights, we return the subtree to save the changes that we've made. Alright, so from here, let's move on to our insertion. So our insertion is going to be a little bit different from our binary search tree. Going over our insert method within our AVL class first, our insert method has a data param, the data that we want to insert within our tree. First, we check to see if we have a root. If we do, we just need to traverse the tree searching for a place for insertion. So this will invoke our insert method within our node class, which is expected to return a node. And then we just pass the data that we wish to insert, as well as the root node as a starting point. If this isn't true, that means that our tree is empty. So we just create a new node with the data being passed in, and save it as the root node. Moving on to the insert method within our node class, we have our two params, data and node. Data being the data we wish to insert, and node being the current node that we're at. First, we check to see if the node is null. If it is, that means we found a place to insert this data at. So we just return a new node with the data that was passed in. Next, if that isn't true, that means we need to continue traversing our tree. So we check to see if the data that we want to insert is less than the data of the current node we're at. If it is, we need to continue traversing the left subtree. And if that isn't true, we test to see if the data we want to insert is greater than the data we're currently at. If it is, that means we continue traversing down the right subtree. Now, once we do all that, we just return the node we're currently at. So this return node will either be saved as someone's left or right child. So that's the basics of a binary search tree insertion. So let's go ahead and give us some space for the AVL code now. After our checks, we need to recalculate the height of the node we're at, since we've inserted a new node. Once we've updated the height of the node, it's time to handle our cases we went over. So we have to keep in mind that we only want to perform a rotation when the node is unbalanced. So either the node has a balance factor of 2 or -2. So in this example, let's say that x represents the variable node and y represents node.left. We know that this is a left-left case, so we rotate right around x having a balance factor of 2 and y having a balance factor of 1. Another example here, this is also a left-left case, where we also need to rotate right around node. Only this time you see that y has a balance factor of 0. Translating this into code, we could say we have a left-left case if the balance factor of node is 2 and its left child is greater than or equal to 0. So this would account for the left child having a balance factor of either 1 or 0. And if this is true, we want to perform a right rotation around x, so node being represented by x. Moving on to the left-right case, following the diagram, we check to see if the balance factor of the node we're at is 2, and if its left child's balance factor is less than 0. If it is, we know how to solve this. First, we perform a left rotation around y. So within the code, y is node.left. And then we go ahead and perform a right rotation around x. So node being represented by x within the diagram. Moving on to the next example, given the following diagram, if the balance factor of x is -2 and y has a balance factor of -1, we know that this is a right-right case. So we just perform a left rotation around x. But we also have another example. So in this case, x is also -2, but its right child has a balance factor of 0. So we can say if the balance factor of x is -2 and its right child is less than or equal to 0, we could perform a left rotation around x. So node being represented by x within the diagram. Last example, given the following diagram, we check to see if the balance factor of the node we're at is -2, and if its right child's balance factor is greater than 0. If it is, we know how to solve this. First, we perform a right rotation around y. So within the code, y is node.right, and then we go ahead and perform a left rotation around x. So node being represented by x within the diagram. Alright, so this is all the code for insertion. Now let's go ahead and walk through an example. So let's say that I was given the following tree. The letters above each node representing the memory address of each node. And we'll go ahead and keep track of the stack to keep track of the main method calls. Now let's say that I want to go ahead and insert 18 into this tree. Executing the code, so we start at our AVL insert method. So let's push this on top of the stack. First, we check to see if we have a root node. We do. So we need to continue our search down our tree. And we go ahead and invoke our insert method within our node class. So let's push this on top of the stack. Executing our insert method, is node null? No, it's not. Is the data we're trying to insert less than the data of the node we're currently at? Yes, it is. So we continue our search down the left subtree. So let's push this on top of the stack. Executing our insert method, is node null? No, it's not. Is the data we're trying to insert less than the data of the node we're currently at? Yes, it is. So we continue our search down the left subtree. So let's push this on top of the stack. Executing our insert method is node null. No, it's not. Is the data we're trying to insert less than the data of the node we're currently at? No, it's not. Is the data we're trying to insert greater than the node we're currently at? Yes, it is. So we continue our search down the right subtree. So let's push this on top of the stack. Executing our insert method is node null. Yes, it is. So we go ahead and return the new node with the data we wish to insert. And then we could go ahead and pop this off the stack. We get returned to our previous insert method, so the new node we created would get saved as the right child of 15. And we continue on executing the code. Calculating the height of 15, we get 1. And now we check to see if we have to rotate. So in the interest of time, we only need to rotate if the node we're at has a balance factor of either 2 or -2. Since the balance factor of 15 is -1, we could go ahead and skip our rotation conditions and go ahead and return 15, popping it off the stack. Getting returned to our previous insert method, we saved node 15 as the left child of 20 and continue executing the code. Getting the height now, node 20 has a height of 2. So getting the balance factor of 20, it has a balance factor of 2. Which means this tree is height unbalanced. Is the left child balance factor greater than or equal to 0? No, it's not. Is the left child balance factor less than 0? So we know it's a left-right case. So first, we perform a left rotation around the left child. So let's push this on top of the stack. Executing our left rotate method, first we'll save the right child of x into y. Next, we'll go ahead and save y's left child. After that, it's time for our rotation. Y's left child references x. X's right child references y's old left child. After the rotation, we now update the height of x, which will give us 0. Now update y's height, which will give us 1. And then we go ahead and return the new subtree, popping this off the stack. So node 20's left child references node 18. Continuing to execute the code, we now perform a right rotation around 20. So let's push this on top of the stack. Executing our right rotation now, we save the left child of x. We save the right child of y. And now it's time for our rotation. Y's right child now references x. X's left child references y's old right child. And now we go ahead and update the heights. So x has a height of 0. And y has a height of 1. After we've updated the heights, it's time to return the new subtree. So let's pop this off the stack. Getting returned to the previous insert method, this has also finished executing, so we just return the subtree that was provided by our right rotate method, popping this off the stack. Getting returned to our previous insert method, so 18 gets saved as the left child of 25, we now go ahead and recalculate the height of 25. So we get 2. Is the balance factor of 25 equal to 2 or -2? No, it's not. So we can skip over all our rotation cases and go ahead and return 25, popping this off the stack. We then get returned to our initial insert call and save node 25 as the root. And since this also has finished executing, we could go ahead and pop this off the stack as well. Alright, so now that we know how to insert within our AVL tree, let's talk about deletion. So for our deletion, the code I'm going to be using is straight from our binary search tree video, except that I'm going to be explicitly passing in a reference to the current node we're at instead of implicitly doing it. And this is just to match the coding style from our insertion method. So going over the delete method within our AVL class, we have a data param, the data we wish to delete from our tree. And we check to see if the tree is not empty. If it's not empty, we'll go ahead and invoke our delete method within our node class. So we'll pass in the data we wish to delete, as well as a reference to our root node as a starting point. Moving on to our delete method within our node class, we have two params, data and the current node we're at. We first check to see if the data is less than the data of the node we're currently at, and if there's a left node. If this is true, we'll go ahead and continue our search down the left subtree. Otherwise, we'll just check to see if the data is greater than the data of the node we're currently at, and if we have a right child. If this is true, we continue our search down the right subtree. Once that's done, we check to see if the data is equal to the data of the current node we're at. If it is, that means that we found a node to delete. Handling the case, if we have 2 children, we find the smallest value within the right subtree. We then replace the data of the current node we're at with the smallest value that we found, and then we go ahead and search the right subtree to delete the duplicate value. Next, we handle the case where we have 1 child. If we have a left child, we just return the left child, and if we have a right child, we just return the right child. In the case of no children, we just return null. Once we successfully deleted a node from our tree, we can copy the code from our insertion method. We first update the height of the current node we're at. We then handle our rotation conditions. So our left-left case, our left-right case, our right-right case, and our right-left case. In the case where we don't need to rotate, we can just go ahead and return the node we're currently at. Alright, so now that we have our code, let's go over an example. So let's say we were given the following tree. The letters above each node representing the memory address of each node. And we'll just go ahead and keep track of the stack to keep track of the main method calls. Now let's say that I want to go ahead and delete 30 from this tree, executing the code, so we start at our AVL delete method. So let's push this on top of the stack. First, we check to see if we have a root node. We do. So we need to continue our search down our tree and go ahead and invoke our delete method within our node class. So let's push this on top of the stack. Executing our delete method, we first check to see if the data we wish to delete is less than the data of the node we're currently at. It's not. We then check to see if the data we wish to delete is greater than the data of the node we're currently at. In this case, it is. So we continue our search down the right subtree, pushing this on top of the stack. Executing our delete method, is the data less than the data of the node we're currently at? This fails. Is the data greater than the data of the node we're currently at? This also fails. Is the data equal to the data of the node we're currently at? This is true. So we found a node to delete. So does this node have 2 children? No, it doesn't. Does this node only have a left child? No, it doesn't. Does this node only have a right child? No, it doesn't. So that means this node has no children. So we could just go ahead and return null. And since this delete method has now finished executing, we could pop this off the stack. We then get returned to the previous delete method and continue executing the code. So we set the right child of 25 to null. From here, it's time to update the height of the node we're currently at. So 25 has a height of 2. Next, we check to see if we have to rotate. So 25 has a balance factor of 2. So that means that our tree is unbalanced. First, we check to see if the left child of 25 is greater than or equal to 0. In this case, it is. So we perform a right rotation around 25. So let's push this on top of the stack. Executing our rotate right method, first we save the left child of x. We then save the right child of y. Now it's time for our rotation. We set the right child of y to reference x, and we set the left child of x to reference y's old right child. After our rotation, all that's left to do is update our heights. So x's height becomes 1 and y's height becomes 2. Next, all that's left to do is go ahead and return this subtree. And since this has now also finished executing, we could pop this off the stack. We then get returned to our delete method, where we also return the subtree that was returned from our right rotate method. And since this has also finished executing, we could pop this off the stack. We then get returned to our initial delete method and save the subtree that was returned to us from our rotate right method as the root. And since this has also finished executing, we could pop this off the stack as well. So that pretty much wraps up this video. I hope you guys learned something, and I hope to see you guys in the next tutorial.